So we had this relationship, and then do you remember what the law of universal gravitation was? Gravitational force equals
G,
big G, universal gravitation constant, very small, M1, M2,
R squared.
good, over R squared, very good. Okay, so then we want to, okay, so we want to do some stuff with this. We want to, first of all, what if we knew,
G.
we could I just gave it to him last period, but let's calculate it. What if I want to know, for example, what the period is for, like, the moon? Okay. Or better yet, we can easily observe the period. If we over a period of, bad word, if we both over a course of a couple of years just plotted where the moon was every day or every night at midnight or something, we wouldn't have to go that long. We could pretty easily figure out that the moon has a period of 27.3 days. Now that wouldn't be a big deal at all for us to do. Okay, so I'm going to do this a little differently this period so I don't get bored. I like to mix things up a little bit. So 27.3 days. What if we want to know how far away then? That should be enough for us to know how far away it is from, well, hang on. I'm getting ahead of myself a little bit here.
I feel like you need to know one of the masses.
Yeah, we'd need no masses, wouldn't we? Okay. So we're not going to be able to calculate this one without having to look up some masses. It's okay. We can do that. Let's do that. So if we know,
Wait, what's 27.3 again? That's G?
Yeah.
And we know that from that one guy, the magnets or the iron.
27.3, this is just by observing the moon, right?
Ah.
Okay, so we know that the mass of the Earth, we weighed it yesterday in class, right? We know how to do that. We didn't actually do it, but we know how to do it. We massed the Earth, and so we know that the mass of the Earth is equal to better look it up. I can't remember what it is. 5.98 times 10 to the 31st? 31st? To 24th. I think it's 31st. Somebody look it up. Google it. Kilograms.
Wait, so how's the big G different from like the little G?
Because the big G is an absolute constant. 6.67 times 10 to the minus 11. It's a constant. It's the same everywhere. Little g is not a constant. It's a pseudo-constant. 9.8 is just, what it is mostly, but it varies from here to there, right? And that's only for our planet at the surface, right? But this is the same every place in the universe. Okay. What is it? Mass of the Earth? You got it? You doing it, Ryan?
These are Jeopardy thing.
Oh.
5.972 times 10 to the 24th kilogram.
Okay. I always remember 90. I wonder why.
That's
It's
okay,
weird.
thank you.
Yeah. To the 20, what was it? 27? 24th. Okay, it's 24. Okay. And then the mass of the moon. So the mass of the moon, that's a little tougher one. We would have to kind of calculate that maybe by knowing what it's made of. So this is a little hokey. We couldn't really do that very easily. Okay, but if we knew, well, actually, we don't need it. Never mind. Because this is equal to the force of gravity. So the force acting on the moon is equal to the moon's, I gotta rewrite this. So I gotta change my scripts here. We'll just call that R, but we're gonna call this M sub E and M sub M, right?
What's M?
M is moon, E is
Oh,
Earth.
yeah.
So the force acting on the moon is going to be equal to its mass times the acceleration, right? Agreed? So, right? Let's do that. We don't need the mass of the moon. We can find the acceleration acting on the moon just by knowing the mass of the Earth, right? Make sense? Okay. We know that this is the centripetal acceleration, right? And centripetal acceleration, we can relate to either period or speed. So let's throw up some stuff from last chapter. Centripetal acceleration is v squared over r. Without looking, can anybody tell me what it is in terms of period and radius?
2 pi.
About 4.
Oh my gosh.
The T squared.
What am I thinking of?
Okay.
There's
Oh,
another
no.
one.
Yeah, there's,
I
it's like
don't
2
know.
pi r.
Okay, and then we have the relationship between, now, the other one is pretty handy. For uniform circular motion, if we want to know the relationship between speed, right, in this case orbital speed, period, and radius, just think of the definition of speed. It's distance over time, right? So speed would just equal, what's the distance going to be?
2 pi r
2
over
pi r. There you go.
over t.
Over the time, which by definition is t. So that's everything we need to know. That is chapter 7 in a nutshell, isn't it?
Mhm.
Minus torque, I guess. Right. Okay. So what can we do with this then? We know that centripetal acceleration is equal to this, right? Capital G, which we know, we calculated it yesterday, right, with our fancy torsional contraption,
Yeah.
times the mass of the Earth, which we know, I'm just gonna call it m sub e, because that's a constant, over the radius, which is how far apart the moon is from the center of the Earth. That's what we're trying to find, isn't it? Right? So which one would we want to use for centripetal acceleration then?
What?
Which one? Which version of centripetal acceleration are we going to use? Yeah, we want to use the one with a t in it, right?
Mhm.
Okay, and because we know what t is, we observed that that's 27.3 days. Okay, we're gonna have to turn that into other units, I guess. And r. Okay, so then we end up with this equaling 4 pi squared r over t squared, right? Okay, so now we got to do a little algebra. What are we going to do? We're going to cross multiply, right?
Mhm.
So we're going to get 4 pi squared r cubed equals g times the mass of the Earth times t squared,
Yeah.
right?
What are we looking for?
We're going to divide by 4 pi squared, right? Because we just want to isolate r. So those go away, and then we end up with r cubed equals that whole thing. So r must be the cube root of all that stuff, right?
Mhm.
Did you try that cross out?
Yeah. Well, that didn't work very well. Okay, now it's crossed out. T squared over 4 pi squared. So we need to do a couple things. The period is 27.3 days, so we'll have to convert that. We can just do that in the calculators. Multiply by, we want to do meters per second, so we have to multiply by 24 and then by 3,600. Does that make sense?
What?
Because there's 24 hours per day, 3,600 seconds per hour,
Yeah.
right? Okay, so when we put all this in our calculator, we're going to get the cube root, so we've got the quantity. Well, we can even use a cube root if we want to. Let's go math, cube root of the quantity, g, which is 6.67 e. Where? Oh, there it is. Second e negative 11. Whoops. Times mass of the Earth 5.98 e 24. It's like battle of these huge numbers. Times t, which was the quantity .3 days, so times 24 to get to hours, times 3,600 to get to seconds. And we're gonna square that whole thing. And then we're gonna close the numerator, right?
Yep.
All that divided by the quantity, 4 times pi squared, gives us that number. So that's the radius in meters, okay? Right, because we used all standard units, right?
Oh, yeah.
Radius of meters of what?
Of the moon, how far it is from the center of the earth. Okay.
How far the center of the moon is from the
Center of the moon from the center of the earth, exactly. Okay, and why did we have to change, real question real quick, I wanna make sure you get this. Why did I have to convert, I couldn't just use days for period.
You want to get to seconds, because seconds is standard.
And why do I need standard units? Why couldn't I have said, oh, well, my answer will be in seconds? Just left it in terms of days. How come? Because if I use,
Well, days are different.
days are different, right? They are, days are different. Days are different, and there's something in this calculation that presumes we're using standard units.
The,
Yeah, the big constants.
Yeah.
Those constants, well, the M wouldn't matter, right? But the G does. The G, that's written in terms of standard units, right? Okay, so we should always just put things in standard units when we're doing calculations. Okay, I'm gonna show you another one here in a second where you don't have to, and you're gonna say, okay, but you're right, there's some instances where we don't need to. And you'll see why. So there it is in meters, so let's put this into kilometers. So let's just divide that by 1,000. And it gives us about 383,000 kilometers. That's a little different than the value the book gives. The book gives a value of roughly 390,000 instead of 383. I don't know why.
Google says it's 384.
384.
Oh, so close.
Okay, so something in there, we used a number, like 27.3 is probably not accurate. You know, it's 27 point, who knows, right? And what else could we have done that wasn't accurate?
We did put 5.9.
G is 6.67, but I only used it to 3 places, you know, and we only used the mass of the earth to 3 places, right? And I used 5.98 because that's the one I always remember from college, but I don't know why that, whatever source said 5.97, so, you know, I don't know. So there's a few, it's off by a little bit, but that's all right. So, close enough, right? So now that's kind of cool. That gives us, that's how far the centers of mass of the earth and the moon are. That's pretty far, right? We'll go ahead and use, you know, I guess being as the problems that I wrote last night used 390,000 because that's what the book says. We'll just use that. That's how we got our 390,000 though, right? That make sense? Okay, so once we know that though, now we can take some shortcuts because now we know we can use, alright, thank you. Alright, what do we got here? What am I supposed to do with this? Oh, this is career day.
Oh.
I wouldn't be.
Am I supposed to know?
I'm
Hang on.
actually excited for it. I
I'm
like
gonna be
not
out.
No, we're gonna jump.
Alright.
I look at her and I'm like.
Because she plays the piccolo too. Are we gonna do that right now?
I don't even know.
Yes.
No, I meant like the...
Oh, no, that's for tomorrow in TA.
Oh, okay.
But she's best.
she really enjoys.
No, I thought we were.
It's very nice.
I was sitting right next to you. Oh, no, you weren't at the honor band.
Thanks for rubbing it in, Ezra.
It was a hotline.
Cause they only want like one piccolo per band. So I never did it.
Equally unrelated.
No, I still have piccolo.
Okay, so here's my question to you then. This is a real important question. I want to explain this. This is the title on my video of what this talk's all about. Is you tell me, think about, how many people have satellite dish at home? Raise your hand if you have
Everyone.
satellite dish. Some
Wait,
people have cable, or that's fine.
It's just one.
Or maybe you opt to, like you probably should, to not do any.
Yeah.
is that
Probably
like
better.
DirecTV
Or
and
just
stuff?
the internet.
Yeah, like DirecTV or
I
or
love TV.
Dish,
Eleni
you do
loves
too.
stuff.
I'm obsessed.
Okay, so I want you to tell me, those of you who have satellite dish, picture your house.
Okay.
In what direction does the satellite dish point?
Oh wait,
No,
no,
it doesn't
sorry.
point that way. It doesn't point that way.
I don't have one.
At an angle.
The one I see.
Well,
the one my
okay,
aunt
but
has
it doesn't
points
point
east.
that way, I promise you. It points, Ezra's got it right.
It points east.
Oh, it's the opposite. Wait, I don't know if I'm
If it's
picturing my
not
house
south,
right.
So that's
Mine's
like-
round.
I'm gonna guess.
It's like
I see
southeast.
it in my head.
So you guys, it would point off like over town, right?
Kind of, yeah.
I think mine points towards
The town's here and it's like,
Rachel's house.
So it's pointing off,
see it in my head.
Southeast.
yeah, okay.
Yeah.
Okay,
Yeah.
And yours points over town, right? That way?
Not what the horse is.
Right, which is how you're pointing.
Yeah.
That's the
That's the
opposite
north.
way, isn't it?
Yeah.
Okay, so what's the commonality here? Where do they all point? Yeah, to the south. Almost, and it could be a little bit southeast or a little bit southwest, but it will never be east, it will never be west, it will never be north in Oregon.
That's weird.
It's
It's on Argentina.
Argentina, it would be north.
Oh, that way it's like more than
Okay, so yeah, what are they, how come?
More
Equator.
satellites are southwest and northwest.
Equator,
How big is-
has to do, okay, that sounds good. It has to do with the equator, but why?
There's more satellites.
It's warm there.
Do they- do they
It's near
put
the core, gravity.
Do they
Oh,
put the,
no.
do they put the satellites over the
You
equator?
trying to sound smart.
Okay, a good question, do they put the satellites, satellites can orbit any place.
Well, yeah,
Right,
but
yeah.
where do they put these satellites? Do they
Okay.
put these satellites?
Yeah, but there's something unique about these satellites that it's pointing at. These satellites, does your dish, is it on a motor drive that tracks satellites?
No.
So how's that work then? Satellites move around the earth, how can it be, how does that work? I mean, it's gotta, oh,
What? Poles?
okay. It's pointing at what we call geosynchronous satellites. It's pointing at satellites that are stationary over the earth. But how could they be stationary over the
Oh,
earth?
they're moving in as fast same speed as.
With
They're
the
more than
orbit.
Okay. They're moving so that their movement places them over the same spot on Earth, right, as they pass around the Earth. So they pass around the Earth, the period would be how long then?
24 hours.
Yeah, one day, right? 24 hours. They would need to pass around the Earth in exactly 24 hours so that they could line up over the same spot the whole time. Okay, but then why do they always have to point south? Why? Why
Are
would you
they
point?
over the equator? Like, is that what they
Yeah,
said?
they are over the equator. But why?
Isn't that where the
That way they
force
can
travel is?
reach.
Why? Well, there's a
I
couple.
just feel like it.
No, there's a couple things. I mean, we don't really need to know any physics at all for this part.
Is it something about the moon?
No.
Okay.
Nothing about the moon.
I thought like a hint from back before.
Whoa.
Ooh, Earth. It's real bright.
Earth.
Makeover.
Very bright.
Yeah.
Okay, have a look. So here's our equator, right?
Right.
Ooh, that's nice.
That's really good.
I think you've done that a lot.
The back line.
So there's the equator.
Just let 'em have some.
Now, if a satellite is going to be geosynchronous, it has to orbit in a place that's stationary over the Earth, right? Okay. Now think about that. The satellite is attracted gravitationally to the center of the Earth, right?
Yeah.
Okay. So the only way, if it were to shine a laser beam back straight down towards the Earth, it would always be pointing right at the Earth's center, wouldn't it? Okay, so let's say that a satellite in geosynchronous orbit, it's a laser that's so intense that it burns a little path, right? Does that make sense? So if the satellite is up here and it's shining its laser down here, the laser's got to probably be red, doesn't it?
Yeah.
So there's the laser beam and it's hitting right there as it's in orbit. Well, if it continued, it would continue down to the center of the Earth if it burned a hole, right? So what if we tried to do this with a satellite that was orbiting so that it would pass over Oregon? Okay. In in order to pass over Oregon, we couldn't, this would be impossible. We couldn't have it hover above Oregon the whole time, because then it would be orbiting a place that wasn't the center of the Earth, right? In order to pass over Oregon, so let's say here's Oregon right there, right? This satellite still has to be pointing at the center of the Earth, right?
Yeah.
Yeah.
Well, then it must be in some kind of an orbit that allows it to do that. But the orbit would have to be an orbit whose center was the center of the Earth. So that's going to have to be an orbit that's going to go like this, right? It's going to go around in an orbit like that, where there's the center. So a little bit later, it's going to be over the South Pole, for example, right? It's got to have a north-south component to its orbit, right? Because you can't orbit in a direct circle over Oregon, because that orbital path isn't centered on the center of the Earth, right? Imagine here's a basketball and here's a hula hoop. The hula hoop, when you place it over the basketball, has to have the center of the basketball in the center of the hula hoop. If I pick the hula hoop up so it's over Oregon the whole time, the center of the basketball is no longer in the center of the hula hoop, right? See what I'm saying?
Yeah.
So, geosynchronous orbits can only orbit around the equator, because that's the only path that's gonna allow them to stay over the Earth and have the center of the hula hoop being at the center of the basketball, right? As a consequence, the space around the geosynchronous ring where satellites can go is sought after real estate in space. Very expensive, very tightly controlled. Does that make sense? I mean, not just anybody, you have to pay a lot of money to be able to put a satellite in geosynchronous orbit, because everybody wants to have one up there, and you know, it's a limited amount of space. So let's figure out, while we're talking about geosynchronous orbit, how high is that gonna be?
How about like, how fast does the Earth tilt like that?
Not fast at all. Very, very slightly, yeah. So let's use this relationship, because this is a quick and easy one, right? We've already calculated that the period of the moon is 27.3 days, and the radius of the moon is about 390,000 kilometers, right? Okay, the moon is just a satellite around the Earth. That's all it is, right? A geosynchronous satellite is another satellite around the Earth. So we ought to be able to make a comparison using this ratio. We should be able to say that T sub S for the period of the satellite divided by the period of the moon squared equals the ratio of R sub S over R sub M cubed, right? We know what the period of the satellite is. It's 1 day, right? What we're looking for, the unknown here, is the radius of the satellite. That's what we want to find. So what's the algebra that we would do to solve for the radius of the satellite?
Cross multiply, divide by
No,
two. There, you can.
First, I got to cube root, don't I? 'Cause I got to get rid of that power. So the first step would be, I'm going to get, let's flip these around. So I'm going to get R sub S over R sub M equals the quantity T sub S over T sub M to what power?
1/3.
Well,
2/3.
2/3,
Oh,
right?
yeah.
Because a cube root is just a 1/3 power, right? Last step, yeah, multiply by the radius of the moon, which we know, okay? And so we end up with the radius of the satellite is equal to T sub S over T sub M to the 2/3 times the radius of the moon, right? So let's do this calculation. Now this time, when I plug stuff in, and let's do that, so we can see what it is we're plugging in. So it's supposed to be equals, isn't it? So that equals the ratio. The period of the satellite is 1 day. The period of the moon is 27.3 days. Do I have to convert those?
No.
How come?
Is it the?
They're
gonna
gonna
cancel.
Yeah, the units cancel anyway, so use convenient units, right? Days. Times the radius of the moon is 390,000 kilometers. Do I need to convert that? No, because I'm just gonna get my answer in kilometers then, which is fine for us, for this problem, right? So what do we get?
The big number.
Yeah, these are, when you talk about gravity stuff like this, where, these are big numbers, I agree. So we get the quantity 1 divided by 27.3 to the power of the quantity 2/3 times 390,000 equals 43,015 and change. So according to this calculation, the distance between the center of the Earth and a geosynchronous satellite has to be 43,015 kilometers. And the radius of the Earth is just a little more than 6,000 kilometers. So it's roughly 37,000-ish, right? 37,000 kilometers above the surface of the Earth. It's pretty high, okay? But it is a little bit limited, right? Okay. Let's calculate, how about next issue. Let's calculate how fast it would have to go. Okay, so how am I going to do that? So we found, let me write that number down. So it was roughly 43,000 kilometers from the center, right? Okay, let's see how fast it's going to go. How am I going to calculate that now? What kind of motion is this geosynchronous satellite going to be experiencing in orbit? Okay, it's gonna be uniform circular motion, isn't it? Right.
Yeah.
When we looked at Kepler's laws, we looked at Kepler's laws yesterday. We saw, what was Kepler's first law? Do you remember?
Same as orbit?
Yeah. What was the shape of an orbit? It's elliptical. Okay. And a circle is just an ellipse. What happens to the two foci of the ellipse to make it a circle? Yeah, they slide together and they become the center, right? Okay, so it's just going to be a symmetrical ellipse. Okay. Second law was, remember that one?
Time.
Is the area
Oh.
Okay, good. So an object, a satellite in orbit, sweeps out equal orbital area in equal periods of time. Okay. And the third one was just this guy, right? This relationship right there. Okay. All right, so we're going to combine that with the idea that in order for this to be a geosynchronous satellite, it has to be in exactly the same spot. So it can't be an elliptical orbit, it has to be the circular orbit, right?
Yeah.
All right, so we know some stuff about circles from last chapter. All the stuff we know about circles, if we exclude torque, is really summarized in about 2 or 3 equations. Right? We know what's the relationship between period and speed and radius.
V equals 2 pi r.
Right, yeah, I think you already told that one to me, didn't you? 2
Yeah.
pi r over t.
That's all I know.
Okay, that's one we know. And then we also know that centripetal acceleration, what's the easy formula for centripetal
V
acceleration?
squared over r.
Good. We could also write that if we substitute as
4 pi r.
Squared.
Oh,
R
r squared. Oh,
over T squared.
Good.
That's all I know.
Okay. All right, so if we combine that with the other equation that you guys told me from yesterday, which you already told me, so I know you know it, this gravitational force is equal to, and let's talk about the gravitational force acting on the satellite, how about, right? So, okay, yeah. Gravitational, I can't remember, I get confused between last period and this period, did we? So we did, okay, we did all this stuff, good. Okay, we did a lot of this work, didn't we? Did we, I seriously get lost with this, did we plug in? And we got that, so we did solve that. We don't,
Yeah.
okay, yeah, we wanna solve for speed this time,
Mhm.
right? So that, what are we gonna do differently?
Use the
We
V
already have
equals.
Right, we have period and, right, okay, we do, don't we? We've got this stuff right here.
Yeah.
Yeah, okay. So we can find speed easily, you're right. Yeah, I knew I didn't have to do all this stuff again. So, we know that, oops, using this, thank you for preventing me from doing that. So we're gonna use this equation. So speed of the satellite is gonna equal 2 pi r, okay, which is gonna be, now we wanna use units here that make sense, right? So let's say, how about kilometers per hour? Does that sound good?
Mhm.
Which I want to see how fast this thing has to go. So r was already in kilometers. Oh no, it was,
43.
yeah, that's right, 43,000. Divided by 27.3 days times, let's multiply by 24 hours per day. And that's gonna give us our answer, right? So that's gonna give us the quantity 2 times pi times 43,015.
And when you have like between pi and 43,000, you don't have to put the times.
Between the 2 and the pi.
Wait, what's the H and the
And
D?
pi and the
Oh, really?
43,000.
Yeah,
Hours and days.
it's like the same
It doesn't
thing
take
in
hours.
Hours per day,
Same as
Hour
variable.
per day?
24 hours per
Yeah,
day.
24
Oh, I
hours
see,
per day. So we
okay.
get hours on the bottom.
And then you
Okay.
cancel the day.
Right,
Gotcha.
right. So 27.3 times 24 gives us an answer of about 412.5 kilometers per hour. Okay,
Oh,
so that's pretty fast.
Wait,
The
what
further
are-
you go away, honestly, the slower something goes. So that can't be right. That absolutely can't be right.
What's it ever supposed to be?
Oh, it's supposed to be T, what?
what? T squared.
T squared, that's gonna make it even smaller though, what the heck?
It's not T squared, we found out.
Oh, you're right.
You did.
Yeah.
Oh, no,
It's
that's
only
right.
on-
We did the math one, I don't know.
Maybe we put
Wait, which one are we using?
You need to double check.
Can I just look how fast is it moving?
It doesn't seem like that's fast enough. That can't be fast enough. There's,
This is for the moon, right?
yeah,
No, it's not for the, it's for the satellite.
for the satellite, yeah.
Oh, the satellite wasn't at 43,000? I thought the moon was.
It looks right to me.
It says a velocity of 3.07 kilometers per second
Is what the,
is what, orbital velocity.
Wait, 3 point what?
Over an hours,
What?
are you sure?
Three
You
point
don't want it to be in seconds.
07 kilometers.
well, but
per
that's, you have to
second.
know that that's just right above the earth probably or something though. Further away you go, the slower it's gonna be, but that's, something is not right there.
Are you sure you don't want it in second?
Or
Well, I mean, we-
days.
That was the
No, we
radius
just-
of the,
The satellite.
yeah,
From
What's
the
going on? That can't be right. There's no way. So you could, I mean, you could almost drive a car that fast. That's, yeah, that's not it.
Oh,
400, like in miles, that's over 200 miles per hour.
That's a pretty big radius though.
Yeah. So you think it's gonna make it, I mean, that can't be right. 43,000, there's no way.
His
43,
mind is blown. It blows my mind that his mind is.
what the heck happened there? That's, I can't see what's going on, but there's no way that's right.
What?
Maybe it's
No.
27.3.
We did all that work.
We are right.
Oh, that's it, of
What?
course. It's one day, it's not the 27.3. Duh, I used the moon.
Oh, yeah.
It's when you know, oh man, see what happens?
That's why I thought it was
That's why I thought it was something.
Yeah,
Oh, you
no,
had
I
it
got
written
it.
down
Oh,
right.
so
You
it's-
couldn't say
So it's just divided by 24. That's gonna work. Yeah, that's gonna be better. Okay.
Okay.
They knew that wasn't right. That didn't make any sense. And that's,
We should all get 100% on our test now because.
'Cause I messed it up.
Oh.
so that's a little better. So it's going 11, that's right. That looks right to me. So over 11,000 kilometers per hour. So that's, in terms of miles per hour, that's still pretty darn fast. I mean, you're going 5,000 miles an hour or something. Okay, hold that thought. 'Cause there's a reason I did that calculation.